Hello everyone again. My name is Naveed Anwar. I am from AIT. You might have seen another talk that we did regarding the modeling of being on a wall, and I at that time I said this is the most simple model that you can think of, where a beam is resting on a wall. But let's go a little bit beyond that and look at a concrete frame where a beam is actually connected to two columns, and those columns are then sitting on foundations. And how can we model this simple frame? It's just two columns and one beam, but now they are reinforced concrete, they are rigidly connected, so they don't have the same modeling issues that we saw in the beam resting on wall, but totally different modeling issues will now come up. And I would like you to concentrate on this problem and see how far we can take it in terms of modeling. So it could be a simple model, which is an elastic model, which will just give you, response in the elastic range. So we are going to take this frame, we are going to apply a horizontal load and see what happens to this frame. And we plan to take this frame as far as we can in the modeling. So starting from very basic and simple model, like linear elastic model, we will create a non-linear model, we will do a pushover analysis, we will even do a non-linear time history analysis on this one, we will put the hinges where it's at various location. We will look at the dynamics, we will look at the non-linearities, we will look at the failure, and so on. So I want to emphasize how much modeling actually can be done even for a simple frame, and the same discussion can then extend to buildings and to bridges and other places. So I think this particular example will serve to demonstrate the strengths of the modeling, as well as some of the weaknesses or areas that are still difficult to model, for example, bond failure and some other things. So we will look into this example in a greater detail than the previous one, because now gradually we would like to start getting into a slightly deeper knowledge of modeling and how it works. So I hope that everyone will find this example interesting in many ways. At the same time, it can be actually used in your real projects and real design work as well. We are going to now look at this frame as a column and two columns and one beam in a greater detail. And this video may have several parts to it, because it may not be possible to cover all of the aspects in just one talk. So we will split it up into 3 or 4 subtopics, and I hope that you can follow them all. So let's start the discussion on challenges in modeling of concrete frames through a simple example, as I mentioned in the introduction. And let's say this simple example is a frame with one beam and two columns. Now, what does it take to model this very simple frame completely? And how can we determine all of the response that might be needed? The structure itself is a reinforced concrete frame, which may have flexural reinforcement. That means for the column vertical bars and for beam horizontal bars, as well as shear reinforcement and some confinement both in the column and beam. So let's say this is designed to resist earthquakes, and it has been designed properly, or it is to be designed properly. So it will be subjected to gravity loads and lateral loads that could be static, could be increasing monotonically, could be subject to reverse of direction or change in intensity, such as wind and earthquake. So we can represent most typical loads by this assumption. So let's see that this is the structure that we have to model. Now this is, let's say it's about 8 meter wide and 4 meter high, just to get some physical dimensions to the structure. And obviously, as a structural engineer, the first step will be for us, most of us, will be to create a linear elastic model in any programs like ETABS or SAP or whatever program that we use. And that model will convert this three-dimensional system with finite dimensions into a simplified line model. And we can see that then we can apply loads on it. So the structure will actually look like a frame model in the program. And we can determine both the deflections and the response for gravity loads, as well as for lateral loads, bending moment, and deflection. So this is easy. Everyone can do that. It's rather simple. We can even do it by hand if we want to do that. So this part is what we mostly do.
Now, let's see that if we take the same frame and we just apply a lateral load, and the gravity load is already applied, and we observe what will be the response if the lateral load increases from 0 to a large value that we do not know yet. So if that is the case, then in a model that we just created, the linear elastic model, in that case, the relationship between deflection or displacement d and the load p will be linear. As you can see from here, blue line represents when we use the gross properties of the beam and column, and the orange line represents if we use crack properties, which many codes will specify. So let's see, as you can see from here, that the stiffness will be very different. For the gross properties, the stiffness will be high. For crack properties, stiffness will be small. And here we just stopped the analysis at a displacement level of 400 millimeter. But in reality, this could continue forever. So really, linear elastic model will continue to give the same linear response no matter how large the load and displacement is. It's quite possible that we apply 1,000,000 kilonewton of load and we get 6 meters of displacement for a frame which is only 4 meter high. So the linear elastic model will not care about the dimensions and the reasonability of the results that it gets, which means there must be something missing in this linear analysis, because that does not seem realistic. What is really missing? And if you really think about it, almost everything which is realistic in a real structure or a real response is missing from this analysis. And this is analysis that does not give us in-depth picture of the response of the structure. Real structure will be constructed by using the drawings that we make for it. The columns will have a finite size. There will be reinforcement here, as I mentioned, both vertical and horizontal. There will be ties, there will be confinement, there will be shear reinforcement, and everything will have some capacity, which means there's a certain amount of moment that the column can take, or a certain amount of shear the beam can take, and so on. Real frame will have finite dimensions, will have finite material properties and strengths, will have a limited deformation and force capacity. So it might actually yield, buckle, damage, or break. And all of this we cannot determine from the linear analysis that we just carried out, because that will give us unlimited displacement for unlimited loads without any of these considerations. A real frame will not be what we model, but will actually look like that. So you can see from here the vertical reinforcement, horizontal reinforcement. So actually this is what will be constructed, and this is the structure that we should be trying to model and get the response of. Let's go one step forward to the next stage and see what is it that we really need to do to handle the complete response. We need to handle the stability of the structure, first of all. We need to make sure that the structure does not fall, does not slide, does not overturn, does not have a large deformation. We need to make sure that the strength and capacities are considered, and we should not be able to apply a load which is unrealistic, or we should get displacement which are more realistic and which are not unlimited. We should be able to determine the damage in the various parts, in the concrete and steel. We should be able to calculate the energy dissipation because of the repeated loading or our seismic input. Long-term effects like creep and shrinkage, we should be able to handle those. We should be able to address the foundation settlement, solid structure interaction here. We should be also able to look at the local failures, for example, bond failure between steel and concrete, and crack formation and so on. And we should ultimately be able to say something about the durability of the structure. How long will it last? Or what are the things that will make it unusable in the long term? So these are some of the considerations that we should be able to handle. Obviously, many of these things are quite complex, even with advanced modeling techniques. So let's start with two of the items in the list, which is stability, strength, and capacity, and see how we can look at these. The first model, which is a stability-aware model, will be able to consider the global buckling of the entire structure, as well as local buckling of parts of the structure. So it should also consider the P delta, the moment magnification coming from the local deformations, and the large P delta, which is the moment magnifications or change in deformations coming from the global displacement. So these are the basic things that we should be able to handle. And we should also be able to handle foundation uplift, type of the foundation, fixed foundation, pin foundation. We should also be able to address overturning, sliding, and large displacement effects. So these are the things that we should be able to do in a model. Let's start again with the first part which I mentioned on the top and see how that will affect our response. So once we include the geometric nonlinearity in the model, so we will include the global P delta, which is the displacement increase because of the large displacements happening. The moments will be magnified, and that will magnify the displacement further. So this P delta effect, which is basically related to the lateral displacement of the structure, we can include those. The local P delta of the column and beam, we will be very insignificant for this example, so we will not consider that. And we will consider two options, the fixed foundation and pin foundation, to simulate different foundation conditions approximately. So if we do that, now we get nonlinear curves or response curves, not linear like last time. That means there is a limit how much load the structure will actually take. If you remember the previous graph, the load could be around 60,000 kilonewton for a displacement of 400. Here we can see that if we consider P delta with fixed foundation, the load carrying capacity will be something like 8,000. And if we use pin foundation, which means the foundation is very flexible, it may only be 1,500 and or so. So now you can see that the P delta effects or the stability of the structure, once you consider that in the analysis, the capacity reduces a lot and deformation is no longer linear, and we cannot apply unlimited loads anymore. This, however, is still not enough because we have not considered the capacity of the members that are involved in this deformation. We are not sure if the members can actually take this kind of load and deformation that we have shown here. So let's go to the next stage, which is the consideration of the capacity of the elements. And in this capacity aware model, we can consider, or we should consider, the reinforcement quantity, its distribution, the cracking of concrete, the yielding of bars, and the failure of concrete at a given strain value or whatever criteria we fix for failure. Still difficult to consider are bond and lap splice considerations, anchorage of reinforcement, local failures in materials, and damage to members and materials due to repeated loading and so on. So let's just consider the first part of this problem for now. How do we define capacity of a frame like this? Normally, the capacity can be defined by using two types of parameters. For a column, we can create the interaction diagram between axial load and moment, and from that, we can also determine the moment curvature for a given load level. So moment curvature, we have already discussed a lot in another video, and the interaction diagram we will discuss separately very soon. So these two important curves give us the capacity definition of the column, and this can include the confinement effects as well as the material properties and material strains and so on. Similarly, for the beam, we can draw or we can determine the moment curvature relationship, so that will determine the capacity. Similarly, we could have a shear and shear force curve that we could define to limit the shear failure, which we haven't considered for now in this example. Using these capacity indicators, capacity information, we can create a nonlinear model using plastic hinges, and we define lumped capacity at specified locations where we expect the failure to occur or capacity to be exceeded. And then we can also consider the stability effects that we already considered in the previous models, that means P delta, and we will use the fixed base for now. And you can use any analysis procedure. For example, nonlinear pushover analysis could be used to study this response. And if we do that, we will get force displacement relationship, something like that. And we see two curves here. One is with P delta and one is without P delta. And as you can see, uh, without P delta, we have a higher capacity. With P delta, the capacity becomes even smaller as the deformation increases. And now you can see very clearly that the structure is actually not able to carry a lot of load. Now the capacity is only something like less than 3,000. The linear elastic model was showing something like 60,000 kilonewton. And now we see that after 2,500 or 2,800 kilonewton load, the structure will start to deform. And if it is including P delta, it will not even reach 2,500. And the load capacity will reduce rapidly as the displacement increases. So this is the important consideration where the capacity of the members comes in and alters the global response of the structure. And we can see clearly that the linear analysis was not able to capture this behavior. Now that we have created the models which were linear and models which were aware of the stability and the models which are aware of the capacity, let's see how do these models really compare with each other. And here you can see very clearly that the linear elastic model that we had first can give unlimited load capacity as the deformation increases. This was not very realistic, so we added cracking in it, and the cracking model gave us lower capacity, but still it was not really going to fail at any point. It will continue to give us that response forever. However, when we included the non-linearity, which was the P delta effect, then we can see that the capacity actually was reduced quite a bit, and it could not go on as much as the linear models. And when we started to add the capacity considerations as well, so we saw that the load capacity of the entire frame actually reduced quite a bit compared to the linear elastic model. And actually the structure will be failing very early on, and the linear elastic response will completely miss all of the realistic response from this structure. If we focus a little bit more on the area which is of interest, because we are very large displacement like 400 millimeter for a structure of 4 meter is a bit too much. So let's see how does it compare with some realistic limits of displacements. First of all, let's look at the serviceability conditions. A lot of people, will consider a drift of 0.5%, which is h over 200 roughly, to be a limit, and that will give us a displacement of 20 millimeter. So if you compare the displacement, the force, capacities at 20 millimeter displacement, you will find that more or less all of the models are giving us the same value. So that means the non-linearity, the stability is not a concern at this low load level or low displacement level of about h over 200 or 0.5% drift. So we get a force ratio between the nonlinear or the real response and the linear response to be roughly 1. And I'm comparing here the cracked section or the cracked response. When we look at the damage limit or damage consideration for a drift around 2%, which is often considered as the point where seismic design is to be, performance-based design and other things have to be considered. So 2% is a rather large displacement drift limit for frames of this kind. And at that level, about 80 millimeter of displacement, we get roughly a force factor of 3. That means the linear elastic response will give us a force value roughly 3 times the actual capacity of the frame if we consider both the section capacity and the stability effects or the P delta effects. And if we go to an even larger displacement, for example, about 4% drift, which is like failure of the structure, 160 millimeter, we will consider that to be the structure has almost completely failed. And at that point, the force factor will be around 8. That means the linear elastic model will be telling us that the structure will fail at a load 8 times more than it really will fail. So this is quite a large number. But at the same time, if you look at these numbers, they look familiar and they are related to the R factors or the structure response direction factors used in many codes. They are of similar order when the frames are designed properly. So the building codes and engineers working on the design for seismic effects are aware of these reductions, and they are incorporated indirectly in some of the factors. But it's important to see that the linear response has its limitations, and it cannot really predict the actual response even for a simple frame like we have considered here. Now that we have done quite a bit of nonlinear analysis, uh, we can see that we have covered a lot of ground. Even though we have considered a lot of nonlinearity aspects, we only actually managed to consider two real effects: stability, strength, and capacity. And we are still missing a lot of the other effects that can be considered for complete understanding of this frame. For example, damage. Sustained damage after a certain loading is applied and then unloaded, or repeated loading, energy dissipation, long-term effects like creep and shrinkage that I mentioned, foundation settlement, soil structure interaction, local failures, and durability. So these are the things that we still haven't considered. If we want to go further, we can actually improve our analysis, nonlinear analysis, make it dynamic, make it more detailed, and we can consider the entire force deformation response, including hysteristics and the damage that comes from repeated loading. And this is something that we will consider next. So in the next videos, we could consider many of the things that we did not finish in this current discussion. For example, we will look at the damage due to repeated loading. We will look at energy dissipation because of the cyclic loading, seismic loading, and so on. We will look at the long-term effects of creep and shrinkage, and also we will look at foundation settlement, soil structure interaction, etc. So with these, we will probably cover most of the effects that we can model. Local failures and durability are still effects that are not easy to model in most of the computer programs, and that we will leave for another discussion. So I hope that you found this discussion useful, and I look forward to seeing you in the next videos. Thank you.